Today, let us look at tangent to a circle. Let us take a circle with center A. The segment AB is the radius of this circle. Now let us draw a line passing through the points A and B. Now let us move this line. Now we have a line CD which intersects the circle in 2 points. Now the line CD is called a secant of the circle and the line segment CD is known as a chord of the circle. Let us move the secant further. We see that the points C and D are coming closer until they coincide at point C. Now this line, which is touching this circle at exactly one point, is known as a tangent to the circle. Now how many tangents can be drawn from this point C? Let us draw as many lines as we can from this point C. We see that most of the line touch the circle at 2 points and there is only one line that touches the circle only at point C. So this circle has only one tangent at the point C. Now how many secants can be drawn from this point C? Recall that a secant is a line that touches the circle at 2 points. So if we take away the tangent, all the other lines are secants to this circle. Alright, let us go back to the tangent at point C. Now let us try to draw a line segment from the center of this circle onto the line. Let us look at segment AE. Let us move this point E on the line and see what happens. As E comes closer to C, the length of this line segment gets shorter. And as it moves away from C, it starts getting longer. It looks like segment AC is the shortest distance between the center of the circle and the tangent. But isn't the perpendicular the shortest distance? So the line segment AC would be perpendicular to the tangent through the point C. Wow! The line segment AC is the radius of this circle. We see that the tangent is perpendicular to the radius at point C. What if this point C was outside the circle? How many tangents could we draw now? Note that there is one line passing through C that touches the circle at point D. And there is another line that touches the circle at point E. So we can see two tangents from the point C on the given circle, tangent CD and tangent CE. Now let us get rid of the other lines and join AD and AE. Now here AD and AE are radii of the circle. And we saw earlier that AD would be perpendicular to the tangent CD. Similarly, the radius AE would be perpendicular to the tangent CE. So we just saw a few interesting things. A line that touches the circle at exactly one point is known as a tangent to the circle. And the radius that is drawn from this point of contact is perpendicular to the tangent. Two tangents from the point C on the given circle. Alright, let us look at a few problems. If tangent CE and CD from a point C to a circle with center A are inclined to each other at angle of 80 degrees, then angle CAD is equal to? Alright, let us draw a circle with center A, and we have an external point C. Why? Because we are going to draw two tangents from this point. Now let us draw our tangents CE and CD. Now these tangents are inclined at 80 degrees. So angle DCE is given as 80 degrees. Now we have to find angle CAD. So let us join a few line segments so that we can see angle CAD. Now recall that angle D would be a right angle. Alright, we have joined the segment AD so that we can see angle CAD. But how are we going to find this angle? We can see another triangle here. So let us join the segment AE as well and see if we can find anything. The line segments AD and AE would be equal because they are radii of this circle. Note that angle E would also be a right angle. And the segment AC is common to both the triangles. We just stumbled upon two congruent triangles. We see the triangle ADC is congruent to triangle AEC due to the RHS property of congruency, right angle, hypotenuse and side. So the angle measuring 80 degrees is getting bisected. Let us label both the smaller angles as 40 degrees. Now let us look at our triangle ACD once again. We know two of the angles. But we know that sum of angles of a triangle is equal to 180 degrees. So let us substitute the values and we find angle CAD as equal to 50 degrees. Now let us see something interesting about the tangents CD and CE. When we look at our two congruent triangles, we also see that side CD would be equal to side CE. That means the tangents from an external point are equal. That's another result to remember. Let us look at another problem. Two concentric circles are of radii 5 cm and 3 cm. Find the length of the chord of the larger circle which touches the smaller circle. We have concentric circles. So let us take center A. Let us draw the bigger circle of radius 5 cm. Let us draw the smaller circle with radius 3 cm. Now let us take a chord DE. Now this chord is not touching the inner circle at all. Let us try again. Oh no! This time the chord is touching the inner circle at 2 points. So let us move it somewhere in between these two chords so that it touches the inner circle at exactly 1 point. Let us move this chord DE so that it passes through the point C. Note that all such chords DE that touch the inner circle at just 1 point would be equal. Can you wonder why? Alright, now let us look at our diagram. We want to find the length of this chord DE. Now we can break this chord into two line segments DC and CE. Now let us try to find the length of DC. So we can join segment AD and we get a triangle ACD. Now this triangle would be a right triangle because AC is a radius and DE is a tangent at the point C. So we can easily use the Pythagoras theorem on triangle ACD. Let us substitute the values. And we find CD is equal to 4 centimeters. Now similarly, we can join the line segment AE and figure out the length of CE. We can apply the Pythagoras theorem on triangle ACE. Or we can also see the triangle ACD would be congruent to triangle ACE. There is a right triangle, there is a common side, and there is a hypotenuse which is equal to the radius 5 centimeters. Now since these two triangles are congruent, we can see that CD is equal to CE and it would be 4 centimeters. So you can use any one of these methods that you like. We can figure out the length of chord DE. Substituting the values, we get DE equals 8 centimeters. Let us look at another problem. Prove that the parallelogram circumscribing a circle is a rhombus. So we have a circle and we have a parallelogram circumscribing it. Had the parallelogram inscribed, then the parallelogram would have been inside the circle. But here it is circumscribing, so it is outside the circle. Alright, we can see that the parallelogram is touching the circle in 4 points. Now recall that tangents from an external point are equal, which means that LC is equal to LI. We can join the segments AC and AI to derive this result as well. You can see that angle C and angle I would be right angles, AC and AI are radii, and the side AL is common. Hence, triangle CAL is congruent to triangle IAL. This confirms that the tangents from an external point LC and LI are equal. Now let us extend this result for the other tangents as well. We can see that KC is equal to KG, NG is equal to NE, and ME is equal to MI. What if we add these segments? Let us rearrange the third one and add. Since KLMN is a parallelogram, its opposite sides would be equal. This gives us KL equals LM. Now since a pair of adjacent sides of a parallelogram are equal, that means the parallelogram KLMN is a rhombus. Recall that all sides of a rhombus are equal.